Happy Wednesday. We're going to go through Unit 9-2 notes together, and I'm super excited, but I just want to warn you, today's going to be a little bit challenging, and so I'm going to go through the whole document, the whole note document with you today. We're going to go over every single bit of information, and if you need any help, feel free to email me or send me a remind, or you could rewatch this video and hopefully it's helpful. So let's get started. So what you need to do is get out your 9-2 notes. You have them on your computer just like I do. And so we're just going to go through it. We're going to be talking about a limiting reagent and a percent yield. So throughout this whole thing, I'm going to be referring to a chemical equation, and we're just going to use the same one we used last Friday, or the last time I saw you guys. And so that was when we took calcium solid, right? We took a solid calcium and we added it to water, and it reacted and we formed calcium hydroxide and H2 gas, and then we got to balance that. So we're good. Okay, so we're going to be referring to this reaction a bunch, or if there's other examples, we'll be looking at those. So the first question after concentration, it says concentration is expressed in molarity, and you're thinking, okay, I know that concentration means how concentrated a solution is, but what in the world is molarity? Okay, and so molarity is pretty cool. It is, so here's molarity. The definition is molarity is equal to the moles of solute divided by liters of solution. Okay, so moles of solute divided by liters of solution. What do I mean by that? Well, let's come over to my other whiteboard, and let's just say we have a beaker full of 50 milliliters of water, okay? And if I put into 50 milliliters of water, let's just say I put in some salt, some sodium chloride at the bottom, and I put in, let's say 10 moles of NaCl. This is 50 milliliters of water. Okay, so I have 10 moles of salt in 50 milliliters of water. What is the molarity? Okay, so here's how we would do it. We would take 10 moles of NaCl and we divide it by the volume of the solvent. But, oh, whoops, not the solution, liters of solvent. Okay, good, caught that? Helpful to have it right in front of my face. We need to divide it by this number, but in liters, not milliliters. So we're gonna have to change that. We'll move the decimal point to the left 3 times, and we end up with 0.05 liters of water. If you divide that, that number will be the molarity, or the concentration of this saltwater solution. Okay, so actually we're just going to practice right now. How many grams of hydrochloric acid are in 100 milliliters of a 0.5 molar, that capital N is molar, solution? Okay, if you look at your notes, I have the conversion factor units laid out for you. We just have to figure out what numbers to put in where. So let's look at our whiteboard. We're first gonna have milliliters. And in our first conversion factor, we have milliliters to liters. Then we have liters to moles. And finally, our last one is going to be moles to grams. Yep. Okay. Okay, well, let's figure out what to put in there first. We always start with the given. And in this example, we start with 100 milliliters. Okay. Do we have a relationship between milliliters and liters? Yeah. That was way back from Unit 1. We know that 1,000 milliliters is 1 liter. Then we need to convert from liters to moles. Do we have a numerical relationship between moles and liters? Oh yeah, it's molarity. We know that molarity is moles per liter. And we know this solution is 0.5 molar, which means it's 0.5 moles to 1 liter of solution. Okay. And finally, we need to know the molar mass of hydrochloric acid. And so the way that we do that is we look at the periodic table. Chlorine is 35.5. If we add a 1, it's 36.5. So it's going to be 36.5 grams per 1 mole. All we need to do is use our calculator. So let's get our calculator out and you can type it in just like I do. First, we start with 100. We're going to divide by 1,000 because it's on the bottom. We're going to multiply by 0.5 since that number is on the top. And then we'll multiply by 36.5 because that number's on the top as well. So we get times 36.5. And our final answer is, for the grams of hydrochloric acid we get, so grams of HCl is 1.82 grams, 1.825, 1.83. Boom, there is your first answer. So let's look at the next note, okay? It says, what is the limiting reagent determinant? So I know what reagent means. It's the same as reactant. And so limiting means, okay, so it's holding me back. It's putting a limit on something. The limiting reagent determines, okay, so I'm just going to write the limiting reagent as LR. This determines how much product you can form, okay? Limiting reagent determines how much product you can form. So it's going to hold you back. It means maybe you've got a ton of water, but you only have a little bit of calcium. So you're not going to be able to produce a bunch of calcium hydroxide and hydrogen gas because calcium would be the limiting reagent. It's holding you back from making a ton of hydrogen gas, which is what you want to make because then it makes a big explosion. All right, so limiting reagent, it determines how much product you can make. So let's figure this out. We're going to do a limiting reagent problem, which you're going to run into a bunch of these in this unit. So how do we determine the limiting reagent? Well, we have to look at a chemical reaction. And in this example, we have solid sodium and solid chlorine. We're combining them together. We need to figure out, if we have 6.7 moles of sodium, how much sodium chloride can we make? And if we have 3.4 moles of chlorine, how much sodium chloride can we make? And one of them will be more, and the other one is the limiting reagent. So let's do this. We are going to test this out. We have 6.7 moles of sodium over here, and 3.4 moles of chlorine over here. We're going to see which one produces more moles of sodium chloride. So let's do this together. We have the balanced equation in our notes. And so we're going to convert moles of sodium, and I'm putting that unit on the bottom because we have one on the top, we're going to cancel out, to moles of sodium chloride. And we know we can do this because we have the balanced equation. So we're going to use the coefficients from the balanced equation right here. We know we need to start with 2 moles of sodium, because there's a 2 coefficient next to the sodium in the chemical equation, and that converts to 2 moles of sodium chloride because there's a 2 as the coefficient next to sodium chloride. And if we do this math, we end up with divide by 2 and multiply by 2. That's going to end up with 6.7 moles of sodium chloride. Okay, perfect. Well, let's check the chlorine gas. We started out with 3.4 moles of chlorine gas, and we're going to convert moles of chlorine gas to moles of sodium chloride. Okay. What is the numerical relationship here? Because we're converting from moles of something to moles of something else, just like on our stoichiometry roadmap, we need to look at the balanced equation coefficients. Chlorine is a blank, so it's 1, and sodium chloride is 2. So we'll just multiply this and we get 6.8 moles of sodium chloride. Wow, looks like if we have 3.4 moles of chlorine gas, we produce more sodium chloride than over here, which means sodium is our limiting reagent because it produces less. It's limiting the amount of product that we can make. If we look at our notes, there's a few more questions. It says, why is sodium the limiting reagent? Well, we just discussed that. Sodium is limiting how much sodium chloride we can make because the amount that we have produces less sodium chloride than the amount of chlorine that we have. The next question says, what do you use to determine how many moles of sodium chloride are produced? What do you use to determine how many moles of sodium chloride are produced? We use the coefficients in the balanced chemical equation to determine the amount of sodium chloride that's produced. And then it says find out how many moles of sodium chloride are going to be produced. Well, we can only produce the amount of sodium chloride that the limiting reagent allows us to produce. So we only need to look at how much sodium chloride is produced from the limiting reagent. So this is our final answer for how many total moles of sodium chloride are produced. Now we're going to look at something that is a little bit different, but has to do exactly with what we're talking about. We're going to talk about percent yield. So percent yield is a measurement that scientists use to determine how much of the product did you make compared to how much you could make in a perfect world. Okay, and so the formula for percent yield is going to be the actual yield divided by the theoretical yield. You take the actual yield divided by the theoretical yield and then multiply it by 100 to get the percent. Okay, so you multiply it by 100 and you'll get the percent. So what is the actual yield? What is this number? This actual yield is going to be the amount that you produce in the lab. What do you produce in the lab? So this is your experimental data. Okay? The actual yield you're going to find in your experimental data. But the theoretical yield is going to be the number that you get when you do the math beforehand. So this is going to be if you use up all the reagent or all the reactant and it produces and it 100% converts into product, that's going to be your theoretical yield. Obviously, probably not going to happen. There's a bug. But we can compare our actual yield to our theoretical yield with our percent yield. Okay, so we're going to do an example of this as well. So let's check it out. We're going to solve a sample problem together. We have the decomposition of calcium carbonate into calcium oxide and carbon dioxide. Okay? And so we're going to be able to calculate the percent yield of calcium oxide. Okay? Now the question says, what is the theoretical yield of calcium oxide if 24.8 grams of calcium carbonate are heated? Okay, so we need to figure out if this is heated, if 24.8 grams of calcium carbonate are heated, how much calcium oxide will we produce? Well, we can solve that. We're going to use the stoichiometry roadmap, and we're going to go from the mass of compound A, or the mass of calcium carbonate, to the mass of calcium oxide. So we'll have to go from the mass down to the moles, across the moles, and up back to mass of the next compound. Okay, so if you want to pull out your stoichiometry roadmap, that might be helpful, but I'm just going to go for it. We want to convert grams to moles. The way that we do that is we convert grams to moles using our molar mass. Now the molar mass of calcium carbonate is 100 grams to 1 mole. Okay, and now we're going to convert moles of this guy, of calcium carbonate, to moles of calcium oxide. So I'm going to say moles on the bottom and moles on the top, okay? Because this is moles of calcium carbonate, and this is moles of calcium oxide. Now we look at the balanced equation for the coefficients, because those are the numbers that we want here, but because they're all ones and it's already balanced, we just put a 1 here and a 1 there. And then finally, we're going to convert moles of calcium oxide into the mass in grams. And so we're going to need to look at the molar mass of calcium oxide. And I looked at the periodic table, and that is going to be 56 grams to 1 mole. And now, to calculate our theoretical yield in grams of calcium oxide, all we need to do is take out our calculator, and we're going to go 24.8 divided by 100, because 100 is on the bottom. I don't need to do anything because it's all ones here, but I'm going to multiply by 56 and get 13.88. I'm going to get 13.88 grams of calcium oxide. And this is our theoretical yield. Okay? So we just solved it using stoichiometry. But now the final question says, what is the percent yield? And so we look back at our percent yield formula. We scroll up. What did we write down? Okay. It's going to be the actual yield divided by the theoretical yield times 100. So I'll look right here. It says the percent yield. What's the percent yield if 13.1 grams is produced? That means that's the actual yield. So I write 13.1 grams of calcium oxide as the actual yield divided by the theoretical yield, which is 13.88 grams. If we multiply that by 100 to get percent, we end up with, well, let's find out. 13.1 divided by 13.88 equals times 100. We get 94.3%. That is, 94.3% is our percent yield. So now you know how to calculate percent yield, and you know how to determine the molarity of a concentration. You know what a limiting reagent is, and you know how to use limiting reagent if we're doing any calculations. So if you need to go back and rewatch any of those, you can. Make sure you either take a picture or submit the digital copy of your notes on Google Classroom, and I will start updating your scores tomorrow. So check out your Aries grades for any changes. You're awesome. Have a great day. It's great to see you bright and early this morning. We're almost there. 2 more days.